afternoon, everyone. Thank you for taking the time to come to my presentation. This is actually my second time at Spark Summit, so it's actually very nice to be back. My first time at Spark Summit was last year when I was only an attendee, but I have the privilege of presenting today as a speaker. So thanks once again. So the title of my presentation is Speeding Up Spark with Data Compression on Xeon+FPGA. So the big motivation for my talk today is big data. So we know the rapid growth in big data has also resulted to processing systems that need to move data from node to node around clusters. And also data compression is a way to reduce this data because when you compress the data, you can actually optimize your application. Forbes predicts that about 60% of organizations are actually using one form of data compression or the other. Compression is a very highly CPU-intensive approach, and therefore it presents the opportunity for acceleration in FPGAs because FPGAs today provide this ability to parallelize algorithms. We also see CPUs that are reaching performance limits. Also, the rising demands in data center performance and the ability to reduce costs and performance efficiency helps us to sort of have this FPGA-based systems. So the overarching idea is that we want to see how we can implement CPUs and FPGAs as a heterogeneous system in order to improve the performance of Spark. Just a little bit about me. I'm a fourth-year PhD student at the University of Florida. My interest broadly is around FPGA systems for big data acceleration in particular. I'm also, as part of my dissertation at University of Florida, my research is affiliated with the Center for Nuclear Research in Geneva. I have had past internships at Intel, and I'm currently at Microsoft Research. So what is an FPGA and why are we looking at FPGAs? For those who are not familiar about FPGAs and what they are, FPGAs are a custom circuit, so you can actually reconfigure the fabric after it's been designed and sent out to the field. They also offer programmability, and the low power and energy efficiency makes them very attractive for specifically data center applications or use cases. In terms of the attachment technology, FPGAs there are mostly two different attachment sort of points. The very two common ones are PCIe attached FPGAs, and nowadays Intel is starting to look at tightly coupled FPGAs. So the tightly coupled FPGAs, the Xeon FPGA is going to be the focus of my talk today. Again, if you're not familiar with Xeon FPGA, it's two processor systems, a CPU and an FPGA on one processing package. The FPGA and the CPU currently share a memory space. The FPGA also supports inline data movement, so you can actually process data on the FPGA before it gets to the CPU. There's also a notion of what is called accelerator functional units. This is the dynamically reconfigurable regions of the FPGA where the user's logic can reside. So now let's look at a few challenges in integrating FPGAs into big data processing systems. This is not only unique to Xeon FPGAs, this is also some kind of challenges that you will see if you are integrating just about any form of FPGA. So number one is the programming model. This is something that is very, you would admit if you're a software developer today, one of the challenges you may be experiencing is how you actually derive the benefits of FPGA systems. So this is really like a mainstream challenge. The requirement of hardware-specific knowledge like RTL. The long synthesis time is also an issue. It takes about orders of hours to actually get RTL to synthesize and to get it onto the FPGA. Once you get that done, the portability, taking the FPGA kernels from one vendor-based FPGA to a different vendor could also be a challenge, right? Another challenge is the software to FPGA interface. For big data systems like Spark that are written in languages that are not native to FPGAs, For instance, Spark, it's based or is written in Scala. To get the Scala-based framework working with FPGA, which is mostly in C, C++, that could be a challenge. And also, when you get that interface working, the data transfer overhead could also impact performance. So that is also one key problem when it comes to FPGA integration to such systems. Another issue is sharing the FPGA amongst multiple threads. Oftentimes, offloading a single thread to an FPGA may not help you derive as much performance benefits. So there's the issue of how you actually keep the accelerator fully utilized in order to derive the full benefits of the FPGA. And finally, reconfiguration, like I mentioned, it's also one issue. Although partial reconfiguration is one way to mitigate this, there are some applications that actually that are intolerable to even a second of reconfiguration time. So as you can see, there seems to be a gap between the software developer and the big data developer. And what did we do to sort of bridge this gap? These are in twofold. So the first, we provide an FPGA accelerator abstraction. So the motivation for this is that we wanted to provide a higher level API written in Java, so that Java-based application developers can easily leverage the FPGA. And we also, in doing this, manage the FPGA to JVM data transfer overheads. And in addition to that, we also coordinate the FPGA and thread coexistence between the CPU and the FPGA accelerator. And then the second part to this is we also looked at how we can create this flexible interface to actually make it easy to interface with Spark. And so once that is achieved, the idea is to make it easy such that you can easily plug in the FPGA accelerator without having to make any modifications to your existing Spark or even Hadoop installations. And so we crafted a solution around those challenges and solutions. We called it Swif, which is a simplified workload intuitive framework. And what Swif is that it provides a flexible hardware-software system where FPGA targeted workloads are first-class citizens. And I will explain what that means in a few slides. But the basic overview of Swif is that you have all these workloads on the left-hand side needing to be accelerated on the right-hand side, as you can tell from the FPGA on the right. And then what Swif does is that it sits in the middle, mediating accesses from your framework to the FPGA. So in this case, we have so you can look at a workload as a task in Spark, right? So what you would do is you would send a Spark task down to the FPGA, and Swif would manage the invocation of the FPGA. It would manage the data transfer between Spark JVM and the FPGA's runtime system. So in this case, we're using Intel's accelerator abstraction layer. And then around that, we created a scheduler which wraps around AAL to sort of provide that flexible scheduling mechanism between Spark JVM and the FPGA's runtime system. And if you're interested, the API would look as follows. So at the very top, you would create a Swif model. By default, it would use an FPGA. And after that, you would create a workload. So in this case, we're creating a zlib compression workload. So this is the notion of having workloads as first-class citizens, right? So this is really our focus. So create a zlib compression algorithm called the workload. And then we assign parameters to the workload. In this case, we have an input array that has the input buffer, and then we create an output buffer assigned it to the workload, and then the array size. And then finally, you say Swif.launch, and then you specify the workload that you created. You could also create more advanced launch and scheduling mechanisms if you use a whole different launcher here. So let's take a look at the compression use case of Swif. How do you actually use this in Spark? So at the very top, we have an application, a Spark application. And then on the right-hand side, we have an FPGA, which is doing the compression, and then decompression is on the CPU. So why compression is on the FPGA is compression, like I mentioned, is highly CPU intensive, whereas decompression is not as much CPU intensive. So it makes sense to offload compression to FPGA and relinquish decompression to the CPU. And so when we started designing this, we looked at a few design models. One of those is to have a plug-in model such that it is easy to swap in and out FPGAs or even the CPU for compression or decompression. So in an instance where an FPGA is not available, you could easily, through Swif, switch to CPU-based compression methods. And we wanted to have a heterogeneity between the FPGA compression and decompression of CPU, because compression and decompression would always go hand in hand. So how would you actually use this in Spark? So first, you would export the library path that points to the native implementations of the FPGA runtime system. Second, you point the class paths for Java to the Java implementation of Swif. Thirdly, you would go into Spark and change the default compression codec of Spark to the FPGA compression codec. And then finally, you would run your application. So number 1 to 3 are only a one-time deal. So if you are running your existing application, you really need to make no change besides pointing to Spark these first 3 pointers. And then you just run your application as usual. So now let's get into a few details of how we actually got this working. To get started, we had to look at how compression is done in Spark today. So on the left-hand side, you see a user buffer, which is needing compression. And on the right-hand side, you see the output buffer of the compressed data. And in the middle, you see the output stream. So how this works is that Spark would stream in data from the user buffer into an output stream. And then you can imagine the compressor at the bottom. You can imagine those arrows being like a piston. So you imagine the piston going up and down. So buffer data goes into the output stream, it is pushed up, it is compressed, it's sent out to the output buffer. So we had to understand this mechanism in Spark before thinking of implementing the FPGA-based offload. So once that was clear, the next thing to do was to look at that CPU implementation as a black box and therefore easily unplug that and plug in our FPGA plugin. So once that was ready, we had to see how we can actually get Spark working with this. So of course, the natural thing to do was to get the FPGA and JVM interface congruent. So like I mentioned before, one of the challenges is the interface between the FPGA and Spark or JVM-based frameworks. So in this case, one thing I would do was to create a JNI interface. So Java native interface would give you this sort of a wrapper system where you could wrap around C, C++ native code with higher level languages like .NET or Java. So we've leveraged JNI to implement this and therefore expose the FPGA native functions up onto Java. The other thing was that for the Xeon FPGA platform, which provided us the benefits of low latency and high bandwidth, we were able to also manage data movement between the JVM and the off-heap memory. So once that was clear, the next thing to do was then to create an interface with Spark. So we implemented 2 different classes, the FPGA compressor and the FPGA compressor codec. The FPGA compressor codec invokes the FPGA compressor. Both classes are extendable Java classes, and they also implement the compression interfaces existed in Spark today. So if you take a look at the snippet on the left, the class called FPGA compressor implements the compressor implementation. So in this case, within this method compress, you would call the Swif interfaces. So you could say swif.compress within that Swif API call here. Sorry about that. And so for the code snippet on the right, in this case, we're trying to implement an FPGA version of zlib. So we create a class zlib FPGA compressor, which actually implements the zlib compressor in Spark, and is based off of the base class on the left. So what you do is, within that compressor call, we only need to do base.compress, which goes around and calls the base class. So this is all we needed to do in order to enable a Spark FPGA interface working with Swif. So how all of this sit together is there are two parts to it. So you can look at this as a full stack. So at the very bottom is the FPGA plugin, and on top of that is the Spark framework. What's most important is the shared Java library layer. So that is the layer that abstracts the FPGA and its lower level runtime system. And then that provides a mechanism to then expose the FPGA to the upper level Spark, to the upper level layer. So that would be compressor and then compressor codec. And then Spark sits on top of that and makes call to this compressor through the codec. And like I mentioned, all you need to do in order to leverage this is pretty much to go into the config, keep pressing this button, and change the default compressor in Spark to this compressor codec. So now let's look at a few optimizations that we actually did in order to make this going. So the first thing was the block size. So in Apache Spark, the default block size is 64 megabytes, whereas in Cloudera it's 128. So we wanted to see what was an efficient buffer size to use when transferring data from Spark JVM to the FPGA memory side. When we actually started this, we looked at a few different buffer sizes, and we found out incidentally that 64 megabytes for Apache and 128 for Cloudera were actually the sweet spots. Other transfer sizes incurred much more overheads. So having established that memory size, we also set the NIO buffer size to the block size. So for our Apache Spark, we were using 64 megabytes for our in-house Spark installation. And so how this would work is that you would have data streaming out from HDFS into the JVM. And then, like I said, this block size is 64, and that buffer is pinned, and then it is transferred eventually, finds its way to the FPGA's buffer, and then computations take place from there. One other thing that we did was to provide a mechanism for sharing the accelerator between various threads. By actually tweaking these buffer sizes, you can control the granularity of the tasks that share the FPGA. So this is one thing that we found interesting. One other thing that we also reuse buffers, because for 64 megabytes, allocating such amount of memory natively actually incurs some cost, especially when you're dealing with a large amount of job, or several jobs. So we had to make sure that we're reusing buffers for different Spark jobs. So essentially, that is how we look at it. You would have the threads actually working together. So over here, you have threads that are waiting after they fetch data from memory, and eventually they find their way to the FPGA, and then now they're ready again, and then they all circle back again. And finally, RDD caching. So we also noticed that by caching data, or the RDDs in memory, the FPGA had much faster access to the data. So look at a few results. So one of the first things that we did was to observe the raw compression performance of the FPGA-based compressor, even outside of Spark. Over here, you can see on the left, for the graph on the left-hand side, the y-axis is the speed up, and then you have the implementations for CPU, FPGA native, and FPGA JVM. And this is using the Calgary and Canterbury corpus, and you can see there's almost no overhead for the JVM implementation, that is the FPGA implementation of compression in Java, when it's been wrapped around with JVM. And we'll see up to 8x speed up over CPU baseline. And then for the graph on the right, the y-axis represents the compression ratio. And of course, we're seeing the same compression ratio for both CPU and FPGA because they run the same compression level, that is zlib level 9. So having obtained this somewhat good enough performance, we wanted to see how this would actually work within Spark. So we looked at a very simple use case. We had a Xeon FPGA server So the block on the white blocks are the Xeon cores, and the FPGAs are the black cores, or the AFUs for the FPGA. For this implementation, we wanted to keep it simple, so we actually had a single node Spark cluster. We focused on RDD compression output. We also looked at a particular workload, TerraSort. So TerraSort is very highly used in most Spark jobs because it actually stresses the data path or the data movement for most of the applications that run on Spark. So the system performance is as follows. So for the graph on the left-hand side, the y-axis again is in seconds. So you can see for a job that took 247 seconds on the CPU, when offloaded to the FPGA, it gained a speed of about 3x, down to 78 seconds. So what's interesting here is even without compression, you're seeing about the same performance here, 78 for the FPGA and 74 for no compression, pretty much. But if you look over here on the graph on the right, you will see that by not compressing, you're actually utilizing 4x the amount of memory versus if you were compressing. So you do want to compress, and you do want to compress on the FPGA in order to gain benefits of both speed up and memory space, so memory footprint. Another experiment that we did was to look at the multi-core scenario. So for this job, this is a 7-second job on a CPU with one thread, or about 30 seconds on FPGA. By offloading 2 threads to the FPGA, you can see the FPGA utilization increased by almost 10 seconds. No surprise in the CPU utilization or the CPU runtime reduced by about 2x, but it's still not able to meet the performance of the FPGA at those 2 threads. So the takeaway point from this is that by offloading up to 2 threads, we're able to increase the utilization of the FPGA while still being faster than the CPU baseline. And one of the other, or finally, the other performance thing that we looked at was the caching of RDDs. So by caching the RDDs in memory, we're actually able to see up to 40x performance improvement for the FPGA. Just to conclude, because I'm running out of time, so with this, I hope that you can see that Java-based frameworks can actually leverage FPGAs, but FPGA implementations require special attentions, and the key to it is really the software to FPGA interface. For our implementation, we've looked at having workloads as first-class citizens where you actually need to optimize the performance of the workload in question, even before integration with the software system. We also gave a concrete case study of how we accelerated a job by 3.2x while also reducing the memory footprint by 4x. This shows potential for large-scale deployment, especially where you have many of these nodes that need to move data from node to node to node. And finally, Swif is an ongoing effort, and more work still needs to be done. For more details, you could, if you're going to be at ISC sometime this month, you could possibly stop by for my talk there. And I'd like to thank Intel for a great internship opportunity, University of Florida, where I go to school at for my PhD, for also the collaboration that they had with Intel in making this work possible. And also thank you again to Intel for supporting my fellowship. So with that, thank you.
All right, we have time for a few questions over here.
Have you thought about using AWS new host types, F1s, for this? Because it fits really well to this whole AWS story that
Right.
Compression is one of the most performance heavy loads, and it's F1s are already in this network.
Yeah, so that's a great observation, actually. So I haven't thought about using compression, this framework in F1. I'm familiar with F1, but I can definitely see how the Swif or just FPGAs in general can actually use compression to accelerate workloads. But that will be something that will be worth trying to see how this would scale within a cloud environment. But great question.
Anybody else?
This one in the back.
Here?
For not familiar with this type of device, how does that, in terms of performance, compare with a GPU?
So the question is, how does the implementation of compression FPGA compare against GPU implementation? Some workloads are more amenable to FPGAs, others are not. Others are amenable to GPUs. I personally have not seen any implementation of compression on GPUs, but it would be nice to benchmark to see what the performance would be. Again, another interesting area to look into. But most of the work that I've seen on compression have been mostly on FPGAs, including my talk, of course.
All right, and let's have one last question.
So yeah, just a couple questions, or two questions really. So did you use the gzip compression algorithm here? Or?
Yeah.
Yeah, okay. And then if you go back to the slide you had for the cluster evaluation, or sorry, the end-to-end evaluation where you had the 3.2x speed up, right? So was this, were all the workers, so how many workers were there first of all?
So for this run here, this is actually one worker.
Okay.
Right, and then for the next one here, this is 2 workers.
I see. So on a standard machine, you might have like 4 or 8 cores or something like that. Do you think like at that point the FPGA would still show an advantage when like 4 or 8 threads were potentially sharing it as opposed to just 1 or 2?
Yeah, so I guess to summarize this question is, how much CPUs do you need to equate the performance of an FPGA? So in this case, we've seen that with 2 threads, with 2 CPU threads, the FPGA is still about 2x faster. So I would imagine that you would probably need about 4 or 8. I'm not sure, just speaking off the bat, in order to equate the performance of the FPGA. But based on this analysis, we've seen that with 2 Spark cores, CPU cores, that is still not enough to meet the FPGA performance, which is still 2 times faster.
Right. And the HARP system you used, did that have, how many CPU cores were on there?
For the HARP system, I believe it's 8. I'm not sure exactly, but in this case, in my experiment, this is only based on 2 cores. We've only used 2 out of the total amount of cores on that particular platform.
Okay, thank you very much. Great talk.
Yep, thanks.
All right, let's give our speaker one more round of applause.